Today's question is how the atom was split for the first time. We are not going to use big words to hide our ignorance. We are not going to use metaphors about the universe or poetry about the dawn of the atomic age. We are going to look exactly at the physical mechanics of this process, strictly and rigorously, with absolutely no fluff. We are going to look at the gears and the levers of reality. We are talking about taking something that the universe spent billions of years fusing together inside the crushing gravitational pressure of exploding stars and breaking it apart on a wooden table in a chemistry lab in Germany in 1938. Imagine you have a locked safe. The walls of this safe are theoretically 1,000,000 miles thick. You cannot drill through it. You cannot blow it up with conventional dynamite. The repulsive forces guarding the core of this safe are so astronomically high that throwing things at it simply causes them to bounce off. But inside that safe is more concentrated, raw kinetic energy than you can possibly imagine. A single piece of matter the size of a golf ball holds enough physical power to flatten a major metropolitan city, or if let out slowly, to provide electricity to that city for 100 years. For 2,000 years, human beings thought the atom was the fundamental, uncuttable building block of the universe. The word atom comes from the Greek atomos, which physically means uncuttable. The dogma of physics all the way up to the 1930s was that you could perhaps chip a tiny piece off an atom, but you could never crack it in half. But then physicists found a trick. We found a loophole in the absolute rules of quantum mechanics and electrostatic repulsion. We did not use a massive, high-energy hammer to break it. We used a ghost-like zero-charge particle that sneaked past the universe's ultimate security system without triggering the alarm. And when it got inside, it caused the structure to tear itself apart from the inside out. If you understand exactly how we did this, you will understand the fundamental forces that hold your own body together right now and the exact mechanism that powers the stars in the night sky. The story of how we actually split the atom is a story of missing mass, rigorous radiochemistry, utterly wrong assumptions by the smartest people on Earth, a walk in the snow in Sweden, and a simple geometric deformation of a liquid drop. Pay attention, because we're going to build this from the ground up. First, let us get our definitions strictly straight. What are we actually trying to split? What is an atom? By the early 1930s, we knew from Ernest Rutherford's experiments that the atom is almost entirely empty space. Rutherford took a piece of gold foil, hammered it down until it was just a few atoms thick, and he shot alpha particles at it. Alpha particles are tiny, positively charged bullets. Most of them went straight through the gold as if nothing was there. But every once in a while, one alpha particle would hit something and bounce straight back. Rutherford famously said it was like firing a 15-inch naval shell at a piece of tissue paper and having it come back and hit you. What did this prove? It proved that all the mass of the atom and all of its positive charge is concentrated in an unimaginably tiny dot right in the center. We call this the nucleus. If you take an atom and blow it up to the size of a massive football stadium, the nucleus, the center where 99.9% of the mass is, would be the size of a single pea sitting right on the 50-yard line. The electrons are just buzzing around in the outer stands, and they weigh practically nothing. So when we talk about splitting the atom, we are not talking about knocking an electron off. You do that every time you rub a balloon on your hair to create static electricity. That is just chemistry. That takes an energy of a few electron volts. It is trivial. We are talking about splitting that incredibly dense, massive P on the 50-yard line. We are talking about splitting the nucleus. Now, look at the nucleus itself. It is a cluster of particles, protons and neutrons. Protons have a positive electrical charge. Neutrons have no charge at all. They are strictly neutral. This immediately presents a glaring, massive physical problem, a contradiction that should make your head spin if you know anything about electromagnetism. You know from playing with magnets that like charges repel each other. Positive hates positive. Protons passionately hate other proton. They push away from each other with an electrostatic force governed by Coulomb's law, and this force gets exponentially stronger the closer they get. In a large nucleus like uranium, you have 92 protons crammed into a space so incredibly small, measured in femtometers, which is 1/4,000,000th of a meter, that the repulsive force between them is absolutely enormous. The electrostatic pressure trying to blow a uranium nucleus apart is staggering. If you scaled up 2 protons to the size of golf balls and put them a few inches apart, they would repel each other with millions of pounds of force. Yet in the nucleus, they sit right next to each other. So why doesn't the nucleus just fly apart instantly? Why does uranium or iron or carbon even exist? Because there is another force at play, a force that operates only at incredibly short subatomic distances. We call it the strong nuclear force. The strong force is exactly what it sounds like. It is immensely strong, roughly 100 times stronger than the electromagnetic force, but it has a catch. It only works over a distance of roughly 1 to 2 femtometers. If protons and neutrons get that incredibly close, the strong force reaches out, grabs them, and locks them together, totally overpowering the electromagnetic repulsion. Protons attract protons, neutrons attract neutrons, protons attract neutrons. Under the strong force, they are completely colorblind to electrical charge. They just want to stick together. Think of it strictly mechanically, that the protons are like high-tension steel springs that are tightly compressed against each other, constantly trying to explode outward. The strong nuclear force is like a massive, unbreakable strip of Velcro wrapped around those compressed springs. As long as the Velcro holds, the springs stay compressed. But here's the critical mechanical detail that explains fission. The strong force has incredibly short arms. It only interacts with its immediate touching neighbors. A proton only feels the strong force from the proton or neutron sitting directly next to it. The electromagnetic force, however, has infinitely long arms. It reaches across the entire nucleus. Every single proton in the nucleus repels every other proton in the nucleus, regardless of whether they are touching or on opposite sides. In a similar small nucleus, like carbon with 6 protons, or oxygen with 8 protons, the strong force completely dominates. Every particle practically touches every other particle, the Velcro is everywhere, and the nucleus is incredibly stable. It takes massive energy to break them apart. But look at uranium, element 92. It has 92 protons and 143 or 146 neutrons, making 235 or 238 total particles. The nucleus is physically large for a subatomic structure. It is so large that a proton on one far side of the nucleus cannot feel the strong force Velcro from a proton on the exact opposite side. The strong force cannot reach that far, but that proton absolutely feels the electrostatic repulsion pushing them apart. Uranium is a nucleus teetering right on the razor's edge of physical instability. It is a drop of liquid that is violently jiggling, barely holding itself together. The Velcro is stretched to its absolute breaking limit, and the compressed springs are pushing back with tremendous unyielding force. To split this atom, you do not need to hit it with a sledgehammer. You just need to add a tiny, precise bit of energy to deform it, to overcome that last little bit of strong force holding the outer edges together. Once you deform the nucleus just enough so that the distance between the two halves becomes slightly larger than the microscopic range of the strong force, the Velcro snaps, the strong force drops to zero instantly. And what is left? Only the electromagnetic repulsion of 92 protons. With the strong force gone, the two halves of the nucleus will repel each other with a violent, catastrophic force, flying apart at a significant fraction of the speed of light. That kinetic energy of the fragments flying apart is exactly what we call nuclear energy. That is the explosion. But how do you add that tiny bit of energy to trigger the break? In the early 1930s, the greatest physicists in the world were trying to smash nuclei using particle accelerators. Ernest Lawrence built the cyclotron in Berkeley. They would take protons or alpha particles, which are essentially helium, nuclei positively charged, speed them up using massive magnets and electric fields, and slam them into heavy target elements. But this is incredibly mathematically inefficient. Why? Because the projectile is positively charged. and the target nucleus is positively charged. When you shoot a positive proton at a uranium nucleus, you're shooting a positive bullet at a massive positive wall. As the bullet approaches the nucleus, the electromagnetic repulsion pushes back. We call this the Coulomb barrier. Think of the uranium nucleus as sitting at the top of a completely smooth, incredibly steep, high-voltage hill. The proton gets close, starts rolling up the hill, and loses kinetic energy, slows down, and right before it hits the nucleus, it is repelled and veers off. It scatters. To actually force a positive particle to hit the nucleus, you have to accelerate the particle to astronomical speeds, requiring millions of volts of electricity, and even then, your chances of a direct, dead-center hit are infinitesimally low. Most particles just scatter off the hill. You are putting 1,000,000 times more energy into running the accelerator machine than you are getting out of the occasional successful collisions. Ernest Rutherford himself, the man who discovered the nucleus, looked at the math of the Coulomb barrier in 1933. He calculated the energy in versus the energy out. He famously and publicly stated that anyone looking to extract practical power from the transformation of atoms is talking moonshine. He considered it a practically insurmountable engineering problem. You could never get more energy out than you put in because the electrostatic shields of the atoms were too strong. Then the entire game of physics changed overnight. In 1932, a brilliant British physicist named James Chadwick discovered a new particle. He proved that there was a particle in the nucleus with almost the exact same mass as a proton, but with exactly zero electrical charge. He called it the neutron. The neutron is the ultimate lockpick in nuclear physics. It is a ghost particle. Because it has absolutely no electrical charge, it does not feel the Coulomb barrier at all. It does not see the steep electrostatic hill. It doesn't care about the 92 positive protons guarding the uranium core. If you shoot a neutron at a uranium nucleus, the uranium nucleus does not push it away. The neutron just casually drifts right through the outer electron shell, drifts right past the massive electrostatic defenses, and falls straight into the nucleus. It is physically drawn in by the strong nuclear force once it gets close enough, falling into the nuclear well without any resistance. This discovery meant you didn't need giant, power-hungry accelerators to pump energy into an atom. You just needed a source of neutrons. In Rome, an Italian physicist named Enrico Fermi realized the profound implications of Chadwick's neutron. Fermi was an absolute master of both theoretical and experimental physics, a rare combination. He decided to use these new neutrons to systematically bombard every single element in the periodic table, starting from hydrogen and working his way up to see what would happen. But Fermi discovered something completely counterintuitive during his experiment. You would think that if you want to smash a neutron into a nucleus, you should shoot it as fast as possible like a bullet. Fermi found the exact opposite was true. Fast neutrons mostly passed right through the target or bounced off without being absorbed. Fermi discovered that if you want a neutron to be captured by a nucleus, you want to slow it down. We call these thermal neutrons because their speed is reduced to the normal thermal jiggling of atoms at room temperature, roughly 2.2 kilometers per second, which is practically crawling in nuclear terms. Why does a slow neutron work thousands of times better than a fast neutron? It comes down to strict quantum mechanics. In quantum mechanics, particles do not behave like solid little billiard balls, they behave like waves. The wavelength of a particle is inversely proportional to its momentum. The de Broglie wavelength equation dictates that the slower a particle moves, the longer and more spread out its quantum wavelength becomes. A fast neutron has a very short wavelength. It acts like a tight, small point. It has to hit the nucleus perfectly dead center to be captured. But a slow-moving neutron has a highly smeared-out wave function. It physically occupies a much larger volume of quantum space. Therefore, from the perspective of the target nucleus, the slow neutron looks like a massive fuzzy object. The probability of the nucleus capturing the neutron, what physicists call the capture cross-section, increases dramatically if the neutron is just ambling along slowly. Fermi accidentally discovered this when he placed a block of paraffin wax between his neutron source and his target. Paraffin wax is full of hydrogen atoms. Hydrogen nuclei are just single protons. A proton and a neutron have almost exactly the same mass. When the fast neutron hits a proton in the wax, it is an elastic collision, exactly like two identical billiard balls hitting each other on a pool table. The neutron transfers almost all its kinetic energy to the proton and stops dead or slows down significantly. If a neutron hits a heavy nucleus like lead, it just bounces off with almost all its speed, like a ping pong ball hitting a bowling ball. But hitting hydrogen slows it down perfectly. So Fermi passes his neutrons through water or wax, so slows them down to thermal speeds and hits his target. They are absorbed beautifully. When a nucleus absorbs a neutron, its mass increases by 1 unit. It becomes a heavier isotope of the same element. But usually, adding an extra neutron throws the delicate internal balance of the nucleus out of whack. The nucleus now has too much energy, too many neutrons for its given number of protons. It is unstable. It is radioactive. To achieve stability, the nucleus undergoes a strictly mechanical process called beta decay. Listen carefully to what happens during beta decay, because this is the root of the great mistake that delayed the atomic age by 4 years. In beta decay, the weak nuclear force causes a neutron inside the unstable nucleus to spontaneously transform into a proton. To conserve electrical charge, because you just created a positive proton out of a neutral neutron, the nucleus spits out an electron which has a negative charge. Think about the accounting here. A neutron turned into a proton. The atomic number of an element is strictly defined by the number of protons it has. Carbon is carbon because it has 6 protons. If it gets a 7th, it is no longer carbon, it is strictly nitrogen. So when a nucleus undergoes beta decay, its atomic number goes up by 1. The element physically transmutes into the next element up on the periodic table. If you bombard element 13, aluminum, it absorbs a neutron, becomes unstable, beta decays, and physically turns into element 14, silicon. This is alchemy, real physical alchemy, dictated by the weak interaction. Fermi follows the strict logic all the way up the periodic table until he hits the absolute end of the line. Uranium. Element 92. Uranium is the heaviest and naturally occurring element on Earth. There is no element 93 in nature. So Fermi applies his proven logic. He thinks, if I bombard uranium 92 with slow neutrons, it will absorb a neutron, it will become unstable. Uranium 93, it will undergo beta decay. A neutron will turn into a proton, and it will turn into element 93. I will have created a brand new artificial transuranic element that does not exist in nature. Fermi performs the experiment in 1934. He irradiates a sample of natural uranium with slow neutrons. He takes the sample and puts it next to a Geiger counter. He detects heavy radioactivity. He precisely measures the half-lives of the radiation coming out of the sample. The decay times, 10 seconds, 40 seconds, 13 minutes, 90 minutes, do not match any known isotopes of uranium. Furthermore, they do not match any elements just below uranium like protactinium, thorium, or actinium. Therefore, by process of elimination based on the known rules of physics, Fermi concludes the radioactive signals must be coming from elements heavier than uranium. He announces to the world that he has successfully created element 93 and probably element 94. The entire scientific community applauds. It makes perfect theoretical sense. Fermi eventually wins the Nobel Prize, largely for his work on these new radioactive elements. But Fermi was wrong. He was absolutely, fundamentally, completely wrong about what was happening inside his uranium sample. He was blinded by the established physics dogma of his time. The absolute paradigm of nuclear physics in the 1930s was that the nucleus was tough. You could only chip away at it. If you hit a nucleus with a tiny particle like a neutron, the energy involved was minuscule compared to the total binding energy of the whole nucleus. You might knock off a proton, you might knock off an alpha particle, 2 protons and 2 neutrons, and you might change its mass by 1, 2, or maybe 4 units. The idea that a single slow-moving neutron could cause a massive uranium nucleus to break completely in half was considered physically impossible, mathematically absurd. It would be like throwing a tiny grain of sand at a massive boulder and watching the boulder neatly cleave perfectly down the middle. It defied common sense. So when Fermi and his team chemically analyzed his bombarded uranium, they only looked for elements that were very close to uranium on the periodic table. Elements 88, 89, 90, 91, 92, 93. They did not even bother to check if lighter elements from the middle of the periodic table were present in the sample, because why would you look for something that is physically impossible? Only one single person in the entire world pointed out that Fermi might be fundamentally wrong. A German chemist named Ida Noddack published a paper in 1934 criticizing Fermi's conclusion. She stated, and I quote roughly, that when heavy nuclei are bombarded by neutrons, it is conceivable that the nucleus breaks up into several large fragments, which would of course be isotopes of known elements but would not be neighbors of the irradiated element. She exactly proposed nuclear fission 4 years before it was officially discovered. She saw the logical flaw in Fermi's assumption, but nobody listened to her. Why? Because she was a chemist, not a nuclear physicist. She did not provide rigorous experimental proof or mathematical models, and the physics establishment, led by giants like Rutherford, Bohr, and Fermi, considered the idea of a nucleus breaking in half completely unjustifiable based on their current energy models of the nucleus. Her paper was ignored, and the world wasted 4 years chasing ghost elements. Let us jump forward to Berlin, late 1938. Otto Hahn and Fritz Strassmann are working at the Kaiser Wilhelm Institute for Chemistry. Hahn is arguably the greatest radiochemist in the world at this time. His longtime physics collaborator, a brilliant theoretician named Lisa Meitner, has just been forced to flee Germany to Sweden because she is of Jewish descent and the Nazi regime has stripped her of her position. Meitner and Hahn had been studying Fermi's uranium experiments for years, trying to chemically isolate and properly categorize these supposed transuranic elements, the fake elements 93, 94, 95. Without Meitner there to guide the physics, Hahn and Strassmann are left to focus strictly on the chemistry. They are performing incredibly precise, agonizingly difficult chemical separations. They take a piece of uranium, bombard it with slow neutrons from a radium-beryllium source, and then try to chemically isolate the radioactive products that are created. You have to understand the scale here. The amount of radioactive product created by this neutron bombardment is microscopic. We are talking about maybe a few thousand individual atoms scattered inside a block of millions of billions of uranium atoms. It is literally invisible and unweighable. You cannot just pick it out with tweezers. To separate these invisible atoms, chemists use a technique involving carrier elements. They take the irradiated uranium block and dissolve it completely in harsh acids. Now they have a liquid soup containing uranium atoms and a few thousand mystery radioactive atoms. They know from Fermi's beta decay logic that the element should be slightly heavier or slightly lighter than uranium. If they suspect the mystery radioactive atoms are, say, radium, element 88, they add a macroscopic visible amount of stable barium to the acid soup. Why barium? Because barium and radium are in the exact same column of the periodic table. They are alkaline earth metals. They have the exact same number of valence electrons in their outer shell. Therefore, they have practically identical chemical behavior. They react to the exact same acids and bases in the exact same way. Hahn adds stable barium to the solution, and then he adds a precipitating agent like sulfate. The barium reacts with the sulfate to form a solid crystal, barium sulfate, which falls to the bottom of the beaker. Because the invisible radioactive radium atoms share the exact same chemical properties as the barium, they get trapped inside the barium crystals. They are carried out of the uranium soup. Hahn then filters out the crystals, holds them up to a Geiger counter, and they click furiously. The radioactivity was carried out by the barium. Therefore, Hahn concludes the radioactive substance must be radium. To get from uranium to radium, the uranium nucleus would have to spit out 2 alpha particles simultaneously after absorbing the neutron. That is highly unusual and energetically difficult, but not entirely impossible under the old chipping away theory. But Hahn is a rigorous, meticulous chemist. He knows that to absolutely prove the radioactive substance is radium, he must now separate the radioactive radium from the stable barium carrier. He must prove they are two different elements. To do this, he uses a grueling technique called fractional crystallization. While barium and radium are chemically identical, radium is slightly heavier. Therefore, radium salts are slightly less soluble in water than barium salts. If you dissolve the barium-radium crystals in hot water and let the water slowly cool and evaporate, the radium crystals will form first before the barium crystals. You filter off the first batch of crystals and they should be highly concentrated with radioactivity. You do this over and over, concentrating the radium. Hahn and Strassmann do the fractional crystallization. They boil it, cool it, filter it. They hold the first batch of crystals to the Geiger counter. The radioactivity has not concentrated. They do it again. They try different salts. They try chlorides. They try bromides. They try chromates. They work day and night in the lab. But no matter what chemical trick they use, no matter how perfectly they execute the fractional crystallization, the radioactivity stays perfectly evenly distributed with the barium. They absolutely cannot separate the radioactive substance from the barium carrier. By December 1938, Otto Hahn is forced to a shocking, paradigm-shattering chemical conclusion. The reason he cannot separate the radioactive mystery substance from the barium carrier is not because his technique is bad, it is because the radioactive substance is barium. Let that sink in. Let the strict mechanics of that sink in. Barium is element 56. Its atomic mass is roughly 137. Uranium is element 92, mass 238. Barium is a medium weight element. It is slightly more than half the weight of uranium. Hahn is a chemist. He trusts his chemistry completely. He knows exactly what is in his beaker. He has proved it beyond a shadow of a chemical doubt. He has radioactive barium. But as a physicist, he knows this is impossible. You cannot shoot a single low-energy, zero-charge neutron into a uranium nucleus and knock off 36 positive protons and 60 neutrons. Where did the energy come from to break the strong nuclear force holding all those particles together? It violates every known mathematical rule of nuclear physics. Hahn is baffled. He writes a desperate letter to Lisa Meitner in Sweden before he even publishes the paper. He writes, "We are coming to the staggering conclusion that our radium isotopes do not behave like radium, but like barium. Perhaps you can come up with some sort of fantastic explanation. We ourselves realize that it can't really burst into barium." Hahn publishes his chemical results in a German journal. He strictly states what he found chemically, but he refuses to state the physics implication. He leaves the physics interpretation blank, stating that as a chemist, he hesitates to take a step that contradicts all previous experience in nuclear physics. He throws the ball into Meitner's court. Now we get to the walk in the snow. This is the moment human history pivoted. It is Christmas time, late December 1938. Lisa Meitner is in a small town in Sweden, staying at a friend's house. Her nephew, Otto Robert Frisch, who is also a brilliant physicist working with Niels Bohr in Copenhagen, comes to visit her for the holidays. They go for a walk in the snowy Swedish woods. Meitner is on foot. Frisch is on cross-country skis. Meitner has Hahn's letter in her pocket. She is obsessing over it. She shows it to Frisch. Frisch's initial reaction is exactly what you would expect from a physicist. He says Hahn must